Hello, welcome to the first day of Chapter 2. We're going to start by measuring relative standing and density curves. Uh, think of it, well, if we start with a data set that has a mean of 42 and a standard deviation of 5 units, find the value that is one standard deviation above the mean. So if the mean is 42, one standard deviation above, that means 5 units above, so one standard deviation above would be 47. If I start at 42 and I find two standard deviations below the mean, I'm going to go back one standard deviation, go back another standard deviation to get down to 32. Now here comes the trickier question. If I have a data with a mean of 42 and a standard deviation of 5 units, how many standard deviations above the mean would 50 be? Well, let's see the distance. We're going to go from 50 down to 42. So that's going to be 8. And we're going to divide that by our standard deviation, which is 5. So that's going to be 8 over 5, which is what, 1.6-ish? Actually, 1.6 exactly. So how I did this is I took my value, I subtracted the mean, and divided it by the standard deviation. Now this is what we call standardizing, when we convert values to standard deviation units. So whenever I talk about standardizing, that means I'm converting something to standard deviation units. So to do that, we take the x minus the mean divided by the standard deviation. And we have a name for it called a z-score. So we'll use these quite a bit in this class. So if I have this set of data and this mini-tab printout, let's find the z-score. Well, the z-score, I take my original value, which is 86. That's this one here. I'm going to subtract the mean, which is 80, and divide it by the standard deviation, which is 6.07. That would be 6 over 6.07, and the answer is something like 0.99. Something really close to 1, just a little bit less than 1. So that means we're one standard deviation above the mean. The mean is right here. So it does make sense that we're going to be above the mean, and it's one standard deviation. Now if I find the z-score for 72, my z-score, I'm going to take 72 minus my mean divided by my standard deviation. So this would be negative 8 over 6.07. So that would be negative 8 over 6.07. Mr. Calculator says it is negative 1.31. Negative 1.31. Now that negative tells us that it's going to be below the mean. So 72, if we look, that's down there. That's definitely below the mean, and it's 1.31 standard deviations below the mean. All right. We need z-scores to compare things that don't seem like they're very related. So if I wanted to see who did better, if student A scored 7 on a math quiz and student B scored 12 on the math quiz. If it's the same math quiz, that's easy to compare those values. Student B did better. However, if they're not the same quiz, we'll need z-scores to see who did better relative to the other people in their class. We could also compare if somebody got a 75% on a history test and a 62% on a science test, which one is actually a better score. This could be an AP Bio class, and this could be an easy history test, and it could turn out that the 62% was much better than the 75%. And we could also say the same thing about if an athlete ran a 400-yard race in 51 seconds and another athlete ran a 100-yard race in 12.5 seconds. That this doesn't mean, since 12.5 times 4 is less than 51, that doesn't mean that athlete B is necessarily faster than athlete A, because they're different races. Same with, we could also compare a 100-yard dash and a long jump using z-scores. And here's how. On a history test with a mean of 40 and a standard deviation of 4, Ed scored 44. On an English test with a mean of 30 and a standard deviation of 6, Alice scored 35. Who did better relative to the other students taking the test? Well, let's take a look. If I look at Ed and then who's the other? Alice. To find Ed's score, what I would do is take 44 minus 40 over 4. So that would be 4 over 4, which equals 1. Alice would score 35, subtract that from 30, divide it by 6, so she is at a z-score of 5, 6. So relative to the other people in the race, in the test, Ed did much better on his test than Alice did on her test. Now, when we have data, sometimes it's nice to have a mathematical model, which is a curve that's an idealized description of the graph. No data will exactly fit this curve because this curve uh, has edges or the data will have edges where the curve does not. A density curve is always above the horizontal axis, and this is big. It always has an area of 1 underneath it. The density curve describes the overall pattern of the distribution. The area under the curve and above the interval of values on the horizontal axis is proportional to all observations that fall in that interval. So what that means is if I have this data set, if I want to find the probability that something occurs between 7 and 8, I find the area underneath that curve between 7 and 8. And if that area is 0.12, that means there's a 12% chance that my data will be between 7 and 8. Now, this is similar to last chapter. If it's a symmetric distribution, the mean and the median will be exactly the same if it's an exactly symmetric. If it's not exactly, they should be close. If it's skewed, the mean is going to be pulled closer to the tail because outliers affect the mean much more than they affect the median. Now, the median of a density curve is the equal areas point. It's the point that divides the area of under the curve in half, where the mean of the density curve is the balance point. It's the point at which the curve would balance if it's made out of solid material. Now, these two symbols for mean and standard deviation are what we use when we're talking about more of a theoretical mean and theoretical standard deviation. It's uh, it's the idealized mean and the idealized standard deviation. We'll learn a lot more about that in the future. Now here, like the balance point, we talked about the mean being the balance point. And this is your homework for tonight. Good luck.